The opening or closing of a door is such a common everyday activity that we really do not pay much attention to it. A closer look, of course, will reveal very interesting physics into this act of opening or closing of a door. When we open a door, or for that matter close a door, we really apply a force on the door by holding a knob or a handle which is located furthest away from the hinges. If you look at the line where the hinges are fixed, the door takes a turn about that line and opens up. Similar thing happens during the closing of a door. So, we are applying a force to pull or push the door, and it is getting turned about the line where the hinges are fixed. That is something very common, every day is happening before our eyes. Now, let us take a look at it. When we open a door like this, we normally apply a pull at the edge which is furthest away from these hinges. And similarly, if we want to open it in the other direction, we apply a push at the more or less similar point. This is because if we really try to apply the pull at a point which is much closer to the hinges, we shall find a difficulty, in the sense we need to really apply much larger force. That is something we can feel. Same thing happens if we want to push it from this, applying the force at this point. So, this point is much more comfortable for pulling or pushing, whereas this point is not, it demands larger amount of force. Does that really mean that we need different amount of force to open or close the same door if our point of application of the forces differ? We shall try to look at this question. The closing or opening of a door essentially refers to a turning of the door about the line of hinges. This turning demands a particular physical quantity which definitely depends on force, but not only on the force. In fact, this is the product of the force and the perpendicular distance from the axis about which this turning takes place. Here we have seen that axis refers to the line along the hinges of the door. So, when we are applying some forces over here, actually this distance, perpendicular distance from the axis, is much larger. So, the product F into d, which is the real demand, F can be smaller since d is larger. But when you shift inside the door, then d gets reduced. So, what happens? If d gets reduced, we need to apply larger amount of force. This particular physical quantity is, which is the product of force and distance, is called the moment of the force about an axis or about a point. This is also known as the turning effect, because this product determines the turning that can be obtained with the help of this product. This is also called torque, and it has got a special role in the situations when we deal with rotational motion. Now, we can understand why we need to apply larger force, because all the doors has a particular demand of moment for opening it up or closing it up. So, if we can provide that moment, then and only then this door will open, and providing the moment, we need to take into consideration two aspects. One, the applied force, and another is the perpendicular distance of the line of application of the force from the axis about which this turning taking place. Larger is the distance from the axis, naturally the force will be reduced, and that is why we try to apply the force at the edges, away from the furthest away from the hinges, so that the demand of the force becomes minimal. A very interesting thing is that the unit of this particular quantity. But before we go to that, let me show you the relationship that we have so far talked about. If we take a look at the unit of this quantity, that is moment of a force, there are two quantities, one is force with a unit of Newton and another is meter. So, the unit of this quantity is Newton meter. Naturally, the question comes up that we already know the product of Newton and meter gives us joule. Should we call it joule? The answer is no. Joule is the unit of energy or work, but Newton meter is the unit of moment of force. They are dimensionally identical, but they are different, because in case of work, yes, it is true, it is the product of a force and a distance, but that distance is along the direction of the force. Here, in case of moment of a force, this distance is perpendicular to the direction of the line of action of the force. So, it remains as Newton meter, and work, although dimensionally identical, that is what is called joule. The important thing about moment is that this particular physical quantity we are really so familiar with in our everyday life. We come across this quantity so frequently, we really once again do not identify it specially, but I would like to show a very simple experiment where we can really highlight the role of the moment of a force and can understand what is the significance of this particular physical quantity. This half meter scale made of wood has been suspended from its midpoint, and this being a uniform scale more or less, this is in a more or less horizontal position with this arrangement. Why is it horizontal? We sometimes tend to think that they are having equal lengths and equal weights, this being a uniform beam on both sides. But if you really look at it, the weights are really acting this way and that way. These two weights, they really cannot balance each other. Weight of this part and weight of this part, they are actually parallel to each other. Then how come they are in an equilibrium position, the scale is in horizontal position? That is because of the fact the weight of this part produces a moment, because weight is essentially force and this is the distance through which the weight acts. So, it produces a moment, and from your side if you look at it, the weight is counterclockwise, from my side it is clockwise. On the other hand, this part is also, weight of this part is acting like this also produces a moment which is counterclockwise from my side, but from your side that is clockwise. So, basically the two moments have been balanced, not the weights. Let us take a closer look at it through this exercise. I am having some iron rings with me. I have tied down 3 iron rings together and I am really placing them on one side of this arrangement. This beam or wooden bar, whatever we call it, I have put it over here. Then I have another arrangement with only one ring, similar arrangement. What I am really going to do that with this, I am really putting it on the other side. Now, you can see on one side we have put on 3 weights, 3 rings, and on the other side we have really put on only one ring, one of similar mass and similar mass. They may not have exactly equal mass, but they are more or less similar. Now, the question is, do we expect any equilibrium or balance? Let us see, can it really be done? Answer is, we can try and see. Now, you can see that, well, we can still achieve an equilibrium with 3 rings on one side and 1 ring on one side. How does it really happen? This happens because what we are balancing here are not the weights of the rings. These weights are force that is acting in this side, and this weight is also acting on this side. And since this is being suspended at the midpoint, if we consider both of them actually, if we forget about this particular ring, this set of rings, they want to turn it in this way about this point, they want to turn this beam. On the other hand, this ring also want to turn the beam in the opposite direction. These two turning effects really get balanced, and that is why we can achieve the equilibrium. So, this comes out to be that we are having 2 different weights, but the moments are equal. If you take a closer look at the scale, you will find the distance covered over here more or less 3 times the distance that has been covered over here. So, the thing is like this, roughly speaking, if we call this mass to be m, this is about 3 m. So, on the left side, or to my left side, 3 m is the mass and 3 mg is the force. This multiplied by, say, x distance is equal to, 3 mg is on the right hand side, it is 3 mg if each weighs m grams, then this one is x. So, on the right hand side the moment is 3 mg into x, on the left hand side it is m into y, and naturally we can expect mg into y. So, g cancels out and m also cancels out, we expect y to be equal to 3x. So, basically what we are balancing here are the moments from these two sides about this central point. Now, if we go to the local shops or in the market, we often find people are using beam balance for selling different items. Those work on same principle, or better I should say on similar principle, and one small difference is there, they use equal arm balance. This is unequal arm balance, because two sides the arms are unequal, although the moments are same. There in the shops they use equal arm balance, and weights are being placed at equidistant from the fulcrum, and in the process once they say put on some sugar on one side and put on a 500 kg weight, 500 gram weight on the other side and get the balance. They say that sugar weighs 500 grams. Actually this g cancels down, and ultimately that becomes the mass of the sugar. So, moments are really being used in our moments of force that are really being used in our everyday life, and quite often we shall find ourselves using this principle and getting so many everyday activities done. Thank you.